H2O will act as a steam and natural gas act as a fuel will produce a synthesis gas, which is CO plus H2, and will enter synthesis gas will enter the methanol converter and produce H2 purge and methanol, also water. Methanol and water will enter the distillation to produce another reaction, which is methanol and water. It can be produced from various sources, which is like coal, natural gas, carbon capture, utilization and storage, renewable electricity, and also renewable natural gas and biomass. Coal will produce a brown methanol. Natural gas will produce grey methanol. Carbon capture will produce blue methanol. Renewable electricity will produce e-methanol, and renewable natural gas will produce biomethanol. This is the literature review of the process and typical process condition for methanol production. So the operating condition that affect the methanol production rate is include the reaction temperature, CO2 fraction in the feed, and the recycle rate of the unreacted gas either to the feed or the methanol reactor. So methanol productivity will increase when the reforming temperature increase, which is due to the high production rate of syngas for both kinetic and thermodynamic reasons. However, when the temperature is too high, the reaction rate will decrease because of the exotonicity of the reaction. So we decide pack-and-pack reactor is a suitable reactor for the methanol production because of high surface area. Reactor need to have a large surface area for the reaction to occur. Next is catalyst support. PBR accommodate a variety of catalyst type, including structure of the catalyst to improve reactor performance. Then heat and mass transfer. The structure of the PBR allows for the efficient mass and heat transfer. Next is recycle of unconverted gases, because PBR is easily incorporate the recycling of the unconverted gas like CO, CO2, and H2, and is crucial to overcoming the restrictions of thermodynamic equilibrium in the manufacture of the methanol. PBR is also flexible and provide operational and optimization flexibility. PBR enabling the development of precise control system that can adjust to various operating situation. The reactor's operating conditions is the pressure is 50 bar, while for the temperature is 520 Kelvin. The reactor's conversion is about 10 until 50% for the CO and 20% for the CO2. And selectivity for the structure reactor is about 80%, while for non-structure is about 54%. The detail of the operating condition of the reactor.
To produce methanol, it is normally start with the gasification of any solid carbon material to produce synthesis gas, such as carbon dioxide, carbon monoxide, and hydrogen, which is subsequently used to produce methanol via catalyst. Synthesis gas is the basic building block for basic chemicals such as methane, ammonia, and hydrogen in various ratios. The steam methane reforming reaction, which is a reaction to produce syngas. Methane plus water will form carbon monoxide and hydrogen, which is syngas. Hydrogenation of carbon monoxide or carbon dioxide with hydrogen will produce methanol. In the reaction 1, only the methanol is produced, which is the desired product. For the reaction 3, water is produced as a byproduct and methanol is the desired product. The hydrogenation of carbon monoxide and carbon dioxide is exothermic and irreversible. Therefore, a low temperature is more favorable to methanol production as it can remove excess reaction heat and shift the equilibrium to produce more methanol. A catalyst plays a crucial role in methanol synthesis because it can facilitating and accelerating the chemical reaction to achieve a higher conversion rate. The catalyst chosen in this reaction is copper oxide, zinc oxide, and aluminum oxide. There is also a side reaction occur in methanol synthesis, which is water-gas shift reaction, and it is mildly endothermic. The purpose is to adjust the ratio of carbon dioxide to hydrogen in the syngas to ensure optimal conditions for the subsequent methanol synthesis step.
For multiple reaction, there will be three reactions involved. Reaction number one is the hydrogenation of carbon oxides, where carbon monoxide react with 2 mole of hydrogen gas to produce 1 mole of methanol. From the calculation, carbon monoxide is the limiting reactant, therefore it will be species A, hydrogen gas will be species B, and methanol will be species C. And the red law is negative R1A equals to KCA CB to the power of 2. For reaction number 2, it will be carbon dioxide react with hydrogen gas to produce carbon monoxide and water. From the calculation, carbon dioxide is the limiting reactant, and the red law is negative R2D equals to KCdCb. And lastly, for reaction number 3, it is also the hydrogenation of carbon oxides, where carbon dioxide react with 3 mole of hydrogen gas to produce 1 mole of methanol and 1 mole of water. From the calculation, CO2 is the limiting reactant. Hence, the red law is negative R3D equals to KCdCb to the power of 3. This is our net reaction and the relative rates. For net reaction, it will involve R1, R2, and R3, and the relative rates is based on all species. The net rates for all species is as follows. From the calculation, concentration of B is 16 times higher than A. Thus, CB naught is equals to CB. Hence, we can cancel CB from the net rates. This is the stoichiometric table, and we found our y n naught equals to f n naught over total f n naught, which is 19. Therefore, we can find our y n naught equals to 0.05263. And the total from the reaction overall reaction is negative 4, and our epsilon is equals to negative 0.2105. Hence, we can input this value into the concentration. Note that this stoichiometry table is based on our overall reaction, which is reaction 1 plus with reaction number 3. Next is the kinetic reactions. From 3 references, we get our formula that will be used in our calculations. For reference 1 is the calculation for conversion, reference 2 is the calculation to get the red constant K, and lastly is the reference for parameter estimates for our K1, K2, and K3.
This is the journey for our calculation. We use programming through MATLAB. Firstly, just using a free add function to display the synthesis route. This MATLAB script identifies limiting reactants in 3 chemical reactions using molar fractions. It calculates required reactant amounts, checks again initial quantities, and determines limiting reactants for each reaction. Next, we define the kinetic rate expressions for 3 reactions. It assumes all reactions are elementary and that the concentration of B is initially equal to Cb naught over Cn naught, implying to Cb naught is equal to Cb. Next, the MATLAB script defines parameters for an isothermal and isobaric plug flow reactor. It includes molecular weight, densities, pre-exponential factors, and activation energy. Then the script lets the user choose a fixed temperature from literature, 5 to 3 Kelvin, or provide a user-friendly input using an if-else function. It initializes parameters and displays the chosen or intertemperature, setting condition for subsequent reactor simulations. Calculates and display initial concentrations, initial flow rates, methanol molar flow rate, and conversion in a chemical reactor. This is also the calculation part for rate constant, catalyst weight, and volume by using spacetime. Here is the calculation part for net rate, selectivity, and instantaneous yield. Lastly, we plot the graph. For the first graph, plot the graph instantaneous yield vs rate of species. The second graph is graph concentration vs temperature.
Based on the literature review, the catalyst is required in order to produce methanol. Thus, payback reactor is suitable to produce methanol. This is the AutoCAD drawing of payback reactor by using 2D wireframe and realistic. By the calculation from the MATLAB, the radius is equals to 1.8 meter and the height is equal to 8.2 meter. The scale used in AutoCAD drawing is 100.